Here's a sample problem 310, which again, if you get this one being a three-dimensional problem and with all the position vectors that are being used, you're really, I think, in my opinion, starting to see things. You have the three cables that are, applying forces at B, C, and D as shown. And what they want you to do is to replace the forces with an equivalent force couple system, or you can just think of it as an equivalent force and a moment system relative to point A. So, the first thing, the first couple things we're going to do is we will determine the position vectors for the points that the forces are acting at relative to point A, okay, and then we'll resolve the forces into rectangular IJK unit vectors, okay. We'll go ahead, we'll add all the IJKs up from all the various forces to give us a resultant, and then we'll go ahead and do the cross product, position vector times force, and come up with a moment, an equivalent moment about point A. All right, so the first thing that they do is they determine position vectors. Again, we are interested in moments about point A. So the way that they write the position vectors, like B relative to A, but the way you should think of, or maybe it helps me to think of this, is think about like you're starting at A and you're walking towards B, or you're starting at A and you're walking towards C, and so on. So the position vector B relative to A, you would be walking in the positive X direction and the positive Z direction, and so there you see that. C relative to A, you're starting at A, you're walking towards C, so you're going in the positive X direction and you're going in the negative Z direction. Again, these are all in the same plane, so you're not going up or down. That's why there's no J's. And then you go D relative to A, start at A, start walking towards D. There's a positive X. These are considered to be in the same plane. You are dropping down in the Y or the J direction 100 millimeters, so that's why you have the negative 100. In this one, if we take our force vector B, since it does not act in a plane, it acts, along some direction that's out there in space. I'm going to have to take my force and 700 newtons and come up with this unit vector, lambda. And the way that we've done this unit vector in the past is we've come up with basically a position vector that it acts at, and then divide that by the overall length. So again, the direction that they're taking this in is down to point E, and they give you X, Y, Z's on point E. So if you, again, if you consider, the X, E is at 150, but B is at 75, so the difference between the two is 75 in the I direction. B is up at plus 100, but we're dropping down to negative 50 in the Y direction, or the J direction, so that's, you're dropping 150, okay? And then K, you are at 50 out from the origin at B, but in the Z direction you're going out 100, so the difference is 50. If you take 75 squared, 150 squared, and 50 squared, and take the square root, it should be 175. So the unit vector, again, 0.429, 0.857J, 289K, and you multiply that by 700. So the force vector of B is 300I negative 600J plus 200K. The other ones, because they act in a plane, aren't really that difficult at all. I mean, the force at C, that sort of acts in the, XZ plane, I guess you could say. So there's a X component and a Z component, all right? And anyway, that's, it acts at an angle 45, cosine of 45. In that, they got a mistake there. They're showing J. It actually should be 45K there. Okay, so that really, the force in the C should end up being 707I minus 707K. There's a misprint on that screen. And then the force in D, again, you sort of do the same thing. D is sort of like in the XY plane. Okay, so you can use the cosine 60 to get the X. You could use the sine of 60 to get the Y or the J. They use cosine of 30. That's okay. So anyway, you have, there 600I and 1039J. So you got the position vectors, you've got the force vectors. You can add up all the forces, I, J, K, just in a scalar fashion. You get the result in there as shown. Okay. As far as the moments go, what you got to do, again, is you got to take the cross product or the vector product from the position vector times the force vector. And again, we've done this a couple times, so it's there as shown, and that gives you a moment of again, these are Newton meters, but it would be 30 Newton meters in the I, 17.68 Newton meters in the J, and 118.9 Newton meters in the K direction. And those are all positive, so again, you can use your right hand rule and sort of get the concept of how those vectors are acting. Anyway, if you can see all the values on that one. Note that there was that one error up there in FC. It's 707I minus 707K. Okay, so that's an error there in the slide. But if you can see that, you're doing pretty well.